In our previous lecture we were discussing about the finite volume discretization of unsteady state diffusion problems, and we will take it up from there. If you relook into the derivations, you will find that we could derive the governing differential equation, or rather we could derive the discretized equation from the governing differential equation in a convenient form: APTP equal to AET plus AWTW plus AP naught TP naught plus B, where in the unsteady state problem you have this additional neighboring term AP naught which takes care of the time neighbor. Now, as we have seen that these coefficients of the discretized equations, they cannot have any arbitrary sign, and we have seen 4 basic rules, and one of those rules is that all the coefficients must be of the same sign. Now, with different choices of the parameter f, if you recall that f equal to 0 was fully explicit scheme, f equal to 1 fully implicit scheme, and f equal to 0.5 Crank-Nicolson scheme. So, we will consider some limiting cases like f equal to 0 and f equal to 1 to begin with. Of course, we can test the case of f equal to 0.5 also and see whether those cases are giving rise to all coefficients of same sign. First, look at the coefficients AE, AW, AP. You can see that f is a positive fraction, Ke is the thermal conductivity which is positive, delta Xe is positive, so AE is positive. Similarly, AW is positive, AP is positive, but you cannot tell anything about AP naught until and unless you are specifying the value of the parameter f. So, let us consider the signs of AP naught and note that we should have AP naught greater than 0. You can also put an equality with the sense that it can be greater than or equal to 0. Now, what happens with f equal to 0? F equal to 0 will give you AP naught is equal to rho Cp delta x by delta t minus Ke by delta xe minus Kw by delta xw. Now, for algebraic simplification, let us consider that Ke and Kw all are same as a uniform thermal conductivity value of the material has uniform thermal conductivity, and delta Xe equal to delta Xw equal to delta x. So, what it means is if we have a grid layout, this is delta x, this is delta Xe, so this is true when all the grid points are equidistant. Then, and if you have the grid point at midway between the faces of the control volume, then you can have delta Xe equal to delta Xw equal to delta x, that is uniformly laid out grid points. So, if that is the case, then we can write this one as rho Cp Now, what are the conditions for AP naught to be greater than 0? Or greater than equal to 0? you must have rho Cp delta x by delta t greater than equal to 2k by delta x, which implies alpha delta t by delta x square less than or equal to half, where alpha is the thermal diffusivity, which is k by rho Cp. In conduction heat transfer, alpha into some characteristic time by characteristic length square is called as Fourier number. So, this is like a grid spacing and time step size based Fourier number less than equal to half. This is called as a stability criteria. We will later on see that what do we mean by stability here. For the explicit scheme. So, what do we mean by stability criterion here, or what do we mean by stability here? Now, when you are doing any numerical calculations, the calculations are susceptible to round off errors, because you may not be able to represent the number with limited decimal points as the correct number. So, there will be some approximate representation of the number because of limited number of digits beyond the decimal point that you can use. Now, that is an error. With calculations, this error can propagate and can get amplified. So, if such round off errors get amplified as the numerical solution proceeds, the corresponding scheme is considered to be, if it is inherent to the scheme itself, it is considered to be an unstable scheme. Now, one of the key requirements of having a stable scheme is that you should have a consequence of the scheme that is physically consistent. That means, if all coefficients are of the same sign, then increasing the temperature at a particular point will ensure that temperature will be increased at all other neighboring points, but not decreased. So, that means despite the perturbations being present, you will get physically meaningful solutions. We will look into a different mathematical angle of stability subsequently, but what we can see here from physical arguments, that we say that this scheme is stable so long as all coefficients of the all coefficients of the discretized equation, algebraic discretized equation, they are of the same sign. Now, what does this criteria effectively mean? So, we have derived a criteria. What will you do with this criteria when you are working out a problem numerically? So, you have to be careful about your time step. What we in general intend to do to get a highly defined solution, we reduce the grid size spacing. So, when you reduce the grid size spacing by delta x by whatever, you can see that the corresponding time step size also should be reduced matching with this requirement. So, you cannot indiscriminately use a large time step size, the time step size is limited by the grid spacing. So, you can clearly see that this ratio is a ratio of two time scales T1 and T2. What is T1? T1 is delta t, and what is T2? Delta x square by alpha. What is delta x square by alpha? It is the characteristic time over which a thermal disturbance propagates by thermal diffusion in a medium. So, alpha is, if you recall, that it is thermal diffusivity. So, it is thermal conductivity relative to the rho into Cp. That means, it is the ability of the material to conduct thermal energy relative to the storage ability of thermal energy. So, that means when you have this alpha is a characteristic, is an indicator of how fast the thermal disturbance is able to propagate within a medium relative to its storage capability. And if delta x is the corresponding length scale that you are talking about, then what is the characteristic time that takes the thermal disturbance to cover that length scale delta x is given by delta x square by alpha. So now what you are comparing is how much is your time step size in resolution as compared to this characteristic time scale of the system. So the system has a characteristic time scale of adjustment of thermal disturbance. So there is a thermal disturbance that is imposed on the system and the system adjusts to itself. So it takes a time, characteristic time to adjust to itself. So this is the characteristic time that it takes to adjust to itself over a length of delta x. So now what is the time step that you choose in comparison to that? Here it says that the time step that you choose in comparison to that must be less than or equal to half of the characteristic time scale of the adjustment of the system with respect to the imposed disturbance. So you cannot indiscriminately use a large time step, but your time step size is restricted by the system's ability to respond to a particular disturbance in thermal diffusion, through thermal diffusion rather. So this is the stability criteria, and once there is a scheme which has a stability criteria, that means you cannot indiscriminately use any large time step, you have to use a restricted time step, then it is called as conditionally stable scheme. That means the scheme will work provided you use a time step size less than or equal to a particular constraint that is determined from the discretized equation. Let us look into the case with f equal to 1. When f equal to 1, you can clearly see that these two minus signs go away and ap naught is positive. So all coefficients are of same sign. That means it is unconditionally stable. So what we have inferred out of this is, with any positive or advantageous effect there is always a limitation. The explicit scheme, that is f equal to 0, had a positive or advantageous effect, that is you could explicitly express the value of the variable in terms of the value of all the neighbors including the time neighbor and calculate it on the basis of individual equations rather than having to solve a connected system or coupled system of algebraic equations. So solution of coupled system of algebraic equations was not necessary for that scheme, but the cost that you have to pay is that you have to use a time step size less than a critical one, you cannot use any large time step size. On the other hand, for the fully implicit scheme you can use any large time step size. Of course, if you want to capture a particular transient that is occurring within a particular time scale, you have to use a time scale less than that one, but that is for capturing the details, but at least to get a physically meaningful solution you do not have to be bothered about the time step. On the other hand, the scheme has a disadvantage or rather limitation if not a disadvantage, that you have to solve the coupled system of algebraic equations for the fully implicit scheme. What about f equal to 0.5, which is the Crank-Nicolson scheme? So if you consider the same case with all the thermal conductivities throughout the domain being the same and uniformly spaced grids, then you have the stability criteria as rho Cp delta x by delta t minus 2k by delta x into half because f is equal to half. So that will give you alpha delta t by delta x square less than equal to 1. It is of course a more relaxed requirement than the fully explicit scheme, but it still has a constraint. So this is also conditionally stable. Sometimes in some literature the Crank-Nicolson scheme is referred to as an unconditionally stable scheme, but the notion that those literatures possibly use is not same as the concept that we are trying to invoke here. Our idea is to see that you get a physically meaningful solution. See, if the scheme is stable, that means if there are oscillations in the numerical solution because of round off errors, those oscillations will be dampened out. But even after the oscillations being dampened out, you may not get a physically realistic solution. The oscillations may get dampened out and the solution may converge to something which is not physically meaningful. So here we are trying to go beyond the mathematical stability requirement. Mathematical stability requirement will just ensure that the oscillations in the solution will die down, but once the oscillations die down, that is the solution is converging to something. Is it converging to the physically acceptable solution that you are looking for? It need not always be. So when you are considering the same sign of all the coefficients, you are ensuring that additional feature also, that is you are having the solution converge to something which is physically meaningful. Now so far we have discussed about the consequences of the discretization scheme from a finite volume discretization angle. Now we would also like to draw a parallel analogy with the finite difference discretization of the time and the space coordinates. So what we will try to do is we will try to see the consequences of time discretization in finite difference. We had briefly introduced the finite difference method earlier and we will take it up from there and see that how we can have different types of schemes which have different behavior. We have made one important remark earlier that the finite difference method is essentially an outcome of a Taylor series expansion of the derivative terms in terms of algebraic differences. Now when you do that, you can do it of course by truncating the Taylor series up to certain number of terms. When you do that, you will get some algebraic equations, but will those equations work or not? In all cases, that is a matter of debate, and that is something that we would like to highlight on. So we would specifically like to see that what are the errors associated in the finite difference discretization or any Taylor series based discretization. To do that, we will consider certain terminologies. First we will consider the terminology consistency. To appreciate the term consistency, so consistency is a characteristic of a numerical scheme. We say that the scheme is consistent. So what we mean by consistent is that when we are discretizing a particular problem, we are representing the behavior that was supposed to be represented by a differential equation with some algebraic equations. So the algebraic equation now has the responsibility of representing the behavior of the system, which is a differential equation in terms of its representation. So there is a conflict that the system behavior was supposed to be represented by a differential equation, now you are representing it by some algebraic equation. In the limit, as the grid spacing and the time step size spacing tends to 0, if your algebraic equation mimics the behavior of the governing differential equation exactly, then we say that the scheme is consistent. So when that is possible? It is possible only when the error incurred because of the discretization is nullified at very small grid size and very defined time step. And when do you expect that to happen? You expect that to happen when the terms that you neglected in the Taylor series turn out to be limitingly small or 0 in the limit of small grid size and time step, and those that error associated with neglecting the terms in the Taylor series beyond a particular term, that type of error is known as truncation error. So, truncation error is what? Truncation error. So, consistency essentially deals with nullification of truncation error as the grid size and the time step in the limit tends to 0. So, nullification of truncation error as grid size and time step size tends to 0 in the limit. Which implies that the discretized equation tends to behave same as the governing differential equation. The difference because of negligence of certain terms in the Taylor series vanishes because the corresponding terms tend to 0 as delta x, delta t all tend to 0. So, a scheme will be consistent. How do you test it? You can test it by checking the truncation error. So, the truncation error will have certain terms which will be functions of delta x and delta t. You put the limit as delta x tends to 0 and delta t tends to 0 separately and see that when you consider them together, that is delta x tends to 0 and delta t tends to 0, the terms which contribute to the truncation error, the terms will tend to 0. Then as if your algebraic equation and the governing differential equation, they are behaving in the same way. So, a scheme has to be consistent, and if it is not consistent, the corresponding inconsistency is because of non nullification of the truncation error in this limit. That is, the truncation error remains even if delta x and delta t are tending to 0. We have to remember that we are not checking the truncation error as a basis for finite size delta x and delta t, because we can understand from common sense that when delta x and delta t are of finite size, truncation error will remain, because we have truncated the Taylor series up to a finite number of terms, that is obvious. But when we truncate the Taylor series up to a finite number of terms but take the limit as delta x and delta t tends to 0, then at least, and in that limiting condition, it should, the truncation error should be 0. So, we are checking the consistency in the limiting condition of delta x and delta t tending to 0 and checking that truncation error has to be 0 at that condition. The next is stability. Now, just like consistency talks about the truncation error, stability talks about the round off errors. So, when you have a number represented by a decimal system, for example, you are using certain digits, number of digits, fixed number of digits beyond the decimal, that is based on the precision of the computer that you are using, but it is not infinite precision, that means you cannot use infinite numbers of digits. So, always there will be a error due to rounding off, and this error can propagate within the calculations and they can amplify. So, if the errors propagate, the round of errors propagate and then can amplify. So, the round of errors in a numerical scheme is like a physical perturbation. So, let us say that you wanted to calculate a number 1/3, but you are truncating it to a finite number of digits beyond the decimal. So, you get 0.3333 up to something. So, 1/3 was the actual thing that you desired for, and this is its representation, and the corresponding difference is like a perturbation or disturbance to the calculation of numbers, and how strongly this perturbation propagates because of, by virtue of the numerical calculations, is also a characteristic of the numerical scheme. So, stability, if the scheme is stable, then it says that there is no amplification of numerical perturbations due to propagation of round of errors. So, by ensuring consistency and stability, we are ensuring that the truncation error and the round of error are not creating an havoc to the numerical solution. And if that is ensured, then for linear problems you can say that convergence is also ensured. So, the next important terminology is convergence. This is what is the ultimate goal that we have for a numerical solution, and the concept of convergence is that in the limit as the grid spacing and the time step size spacing tends to 0, the numerical solution will tend to the exact solution. Now there is a very important theorem which is known as Lax equivalence theorem, which states that, I am not going to state the theorem in a very formal way, but which essentially means that for linear problems consistency plus stability, if you can ensure these two, this will automatically ensure that there is convergence. So, consistency plus stability implies convergence, but very importantly only for linear problems. For nonlinear problems, consistency plus stability may not ensure that there is convergence. One of the key reasons is that for nonlinear problems you could have multiple solutions. So, it is not automatic that for nonlinear problems consistency plus stability together will ensure that there is convergence. So, for nonlinear problems what you do? Usually for nonlinear problems we test convergence in this way. We test the problem with a particular grid size and time step, then we go on reducing the grid size and reducing the time step, and we come to a stage when we see that even if you reduce the size of the grid, even if you reduce the size of the time step, that is further refinement of the grid and refinement of the time step, the solution does not get refined anymore. We say that the solution has become grid independent. And time step independent. So, a grid independence or time step independent study is what is required for a nonlinear problem. If you just have a consistency and stability, that does not automatically ensure convergence for a nonlinear problem. And when we will be doing the full solution of the Navier-Stokes equation, we should keep in mind that because those are nonlinear equations, essentially consistency and stability will not just be enough, we have to check the grid independence and time step independence for solution of such problems. So, we have now got a fair idea of the sources of errors that could be there in a discretization method, and in particular in reference to the finite difference scheme. Now, let us look into certain examples of finite difference schemes and see that how do these errors matter. So, we will consider finite difference scheme for unsteady, one dimensional unsteady diffusion type of problems. Just the corresponding cases on finite volume we have studied, the similar problems with finite difference now we will study. So, finite difference schemes on one dimensional unsteady state diffusion problems. So, the governing equation is this one, where we have assumed a constant thermophysical property, that is density, specific heat and thermal conductivity all are constants. So, assume constant properties. So, you can write where alpha is k by rho Cp, which is the thermal diffusivity which we have discussed physically also. Now, this prototype equation has a time component in it and a space component in it. So, depending on the differencing scheme that we can use for the time and the space, there are different finite difference schemes. So, if you recall that we had different types of finite difference discretization, like forward difference, backward difference, central difference, like that. So, for example, we can use a forward differencing for time and central difference for space. So, that we call as FTCS, forward FT for forward time and CS for central space. So, forward time central space. So, let us write the corresponding Taylor series expansions. While doing so, what we will do is we will use some notations that are common to finite difference. What are these notations? We consider one grid point, which is the grid point P that we were considering for the finite volume. The same we will use an index I plus 1 for E, I minus 1 for W. So, just to give the analogy of the nomenclature, and superscript N for current time and N minus 1 for previous time and N plus 1 next time. So, we can write T I n plus 1. What is T I n plus 1? This is T at time t plus delta t, actually at the grid point I, that is at x. So, I is x, this is x plus delta x, this is x minus delta x. So, T I n plus 1 is equal to, so we are writing, keep in mind that we are writing t at time t plus delta t, we can write it in terms of t at time t. So, we can write this as T I n. So, this is t plus delta t, this is t, and this is, sorry, this is t minus delta t, and this is t. So, T I n plus 1 is equal to T I n plus if we consider the higher order terms, that is of the order of delta t cube. So, we can write minus plus of the order of delta t square. Order does not get changed with sign. So, it is just division by delta t makes it order of delta t square. So, if you now truncate the Taylor series up to this term, then this is the representation of the forward difference for the first order time derivative. What about the second order spatial derivative? So, when you consider the spatial derivative, see, when we consider the time derivative, we kept the spatial position as constant I and change the time. So, here for the spatial derivative we will fix the time fixed, keep the time fixed and vary the spatial coordinate. So, T I plus 1 n is equal to T I n we are not writing superscript n everywhere, but it all are with superscript n. Okay. Similarly, T I minus 1 n is T I n with a minus sign, now it will be. So, delta x becomes minus delta x, that is the only change. Now, if we add these two, T I plus 1 n plus T I minus 1 n is equal to 2 T I n, then plus del square T del x square I into delta x square, cube terms will go away, fourth order term will remain, delta x4 by 12, then fifth order terms will cancel. So, what will remain is of the order of delta x6. Which one? Which one? No, we have not yet divided by delta x square. This is alright, we have not divided this by delta x square. So, next step will be to divide both sides by delta x square. By delta x square minus delta x square by 12 plus of the order of delta x 4. So, here also we will be truncating it up to this one, which is the central difference scheme for the spatial second order spatial derivative. So, let us now substitute these expressions in the governing differential equation. So, the time derivative T I n plus 1 minus T I n by delta t minus let us write it with a different color to indicate that this is an error term, minus del 4 t del x 4 delta x square by 12 plus of the order of delta x 4. So, the terms that we have written with black color are the terms that are going to matter. There is alpha in the right hand side. So, let us multiply alpha with all the terms in this way. So, the terms that are going to matter for the discretized equation are the terms which are written in the black color, but the terms which are written in the red color are important because they can give rise to the understanding of the errors because of omission of those terms. So, let us do that analysis. Let us try to write. Let us first consider, interestingly, these two terms, this term and this term. Now, this particular term, fourth order derivative of temperature with respect to x, that you can attain or that you can obtain by differentiating the governing differential equation twice more with respect to x. So, governing differential equation, if you partially differentiate it twice more with respect to x, then what this will give? Similarly, you can differentiate the governing differential equation once with respect to time to get del square t del t square. So, governing differential equation, if you partially differentiate it with respect to time, you will get okay. So, what we can conclude from here? We can find a relationship between the first leading order term because of truncation with respect to the time discretization and the first leading order term because of the truncation with respect to the spatial discretization. So, we can write del square t del t square is equal to alpha del cube t del t del x square, that is equal to alpha square del 4 t del x 4. Just check whether this is all right. So, if you compare this, let us call it term 1 and let us call it term 2. So, term 1 minus term 2 is what? Is equal to alpha square del 4 t del x 4 into delta t by 2 minus alpha delta x square by 12 del 4 t del x 4. So, if you take alpha del 4 t del x 4 as common, then here you have alpha delta t by 2 minus delta x square by 12 in the bracket. So, you can see that if this term in the bracket is not equal to 0, then what is the order of accuracy of this discretization? Order of delta t is the error for time and order of delta x square for space. So, first order in time and second order in space, but to understand what is that but, we have derived this particular term. Now, if you see that if this term becomes 0, then it becomes of the order of delta t square for time and of the order of delta x4 for space, because then these are cancelled. When term 1 is equal to term 2, these terms in the box in the two sides they get cancelled. When do they get cancelled therefore? They get cancelled, this is 0 when alpha delta t by 2 minus delta x square by 12 equal to 0. That means alpha delta t by delta x square is equal to 1 by 6. Of course, this is a possible choice. So, one can make a choice of alpha delta t by delta x square equal to 1 by 6, then this term will become 0 and then it will be of the order of delta t square with respect to time and of the order of delta x4 with respect to space. Okay. So, this is about the temporal and spatial accuracy of the method. The next question comes that is the scheme consistent, number 1, number 2 is the scheme stable. So, we will try to give answers to these questions. In today's class we will look into the consistency of the scheme and in the subsequent lecture we will look into the stability of the scheme. So, is it consistent? When we say that it is consistent, we say that it is consistent when in the limit as delta t and delta x tends to 0, the truncation error tends to 0. So, what is the truncation error? The truncation error is represented by the red colored terms which are there in the two sides. So, if you make delta t and delta x tends to 0, then obviously they will in the limit be tending to 0. So, some expression which has directly been derived from the Taylor series automatically ensures that the truncation error becomes 0 as delta t and delta x tends to 0. But if somehow you want to temper the expressions that you get from Taylor series expansion, we will see there are certain schemes which attempt to do that they tend to temper the expression that you get from the Taylor series in an effort to achieve something more special, and in that way they can create problems with respect to consistency. But here it is simply an outcome of the Taylor series based expansion of the derivative terms, and therefore it is true that it is a consistent scheme. The next important point that we will try to assess in the next class is that whether the scheme is stable or not. And what do we mean by a stability here is that if you have a perturbation in some numerical value say of the temperature at a particular grid point, then does that perturbation get amplified with time. So, as you proceed or march ahead with time, remember these are all time marching schemes. So, as you march ahead with time you may see that those errors are propagating and the errors are therefore getting amplified. So, we have to find out a mechanism that will tell us mathematically whether the error will get amplified or the error will die down, and that we will take up in our next lecture. Thank you.